Okay, moving right along, we're going to go and talk about how the heart works a little bit. Physiology. So the heart's kind of interesting because it has its own independent source of nerve impulse. We talked about that a little bit. So it has a place here called a pacemaker, the sinoatrial node, right here up here by the atrium, and that's on the right atrium, and it has it releases an impulse about 60 to 70 times per minute. And then that impulse here causes a little contraction of the atria as the blood gets pushed into the ventricle. That's kind of good because we push it along, we push it forward. And the impulse itself gets transmitted to the atrioventricular node. That's a place right here between the atria and the ventricle. And that's the AV node. And from there, the impulse gets amplified and goes all the way down and spreads through the ventricles. So then the ventricles can contract nicely in unison, all the muscles contracting together. And we call that the bundle of His, where the impulse is carried down through the interventricular septum into the right and the left bundle branches down in here, and then into through the Purkinje fibers, which are further down here, coming up on the outside of the ventricle. So that's sort of the conduction system itself, the anatomy of how it looks. And so it has its own pacemaker. So that means the cells actually by themselves, if there's energy available, they just pump. The heart just pumps. It doesn't need the brain to do that. The brain is here to influence it. So we have autonomic nerves, automatic stuff. The autonomic nervous system controls all the stuff you don't think about. So that influences the contraction, and it influences the frequency, the force of the contraction, the frequency. That can do that. The interesting thing is the stimulation is rhythmic in fashion, and we talked about that before. That is because when the impulse goes through the heart muscle, it pretty much penetrates all the muscle cells together because we have the gap junctions there. So the ions can go through the heart cell walls of the heart muscle into the neighboring cells. And so the function of having that contraction coming together as one is known as a functional syncytium. So that's an interesting thing of the heart muscle. Now you could take a heart out, as long as it's got energy, it's going to contract. Kind of goofy, but it does it. And then here, this slide shows us the electrocardiogram, the EKG or the ECG. And it shows us the heart's electrical impulse. It's a diagnostic procedure that helps us understand the development, the spread, and the return of the electrical impulse over the myocardium, the heart muscle. It allows us to help give us position of the heart, give us heart rate, and give us the cardiac rhythm. So it's good for that. So we have a few things. You've probably seen these things. So you have like a line that goes, and then there's a little bump, boop, and then it goes, and then there's a little dip, up, and a big mountain, and a bigger valley, and then it comes back to one more bump, a bigger bump. So we can name all these bumps. So we're very innovative. We go down the alphabet. So we start with the P. I don't know why we start with the P. But the first thing, that first bump, is the P wave. And the P wave is the spread of the electrical impulse over the atria. So see, that's not that big. That's the pacemaker doing that. And then the QRS complex, they call that. That's the beginning when the ventricle start exciting. So when the ventricle gets stimulated, that's the AV node, and then down the bundle of His, down, etc., through the bundle branches and then the Purkinje fibers. That's a big impulse. And then we come back to normal, and then we have one more bump, up, a T wave. And the T wave actually means, since it's an electrical impulse, it's a repolarization. What that means, it's a resetting of the situation that has happened with all the ions that go in and out and fluctuate. So when a nerve impulse travels, we have an exchange of ions, because ions are charged molecules, so they can carry a charge with them. And so we send a lot of ions from one side to the other side of a cell membrane, and that carries a charge with it. So that's an electrical That's an electrical signal, yes, but those are chemicals. So the chemicals are totally out of whack after the impulse happened. And so they have to be reshuffled real fast so we can do the next impulse. So the T wave is showing us the reshuffling of these ions to recorrect the chemical imbalance created by the QRS complex, the ventricular depolarization, the contraction or the stimulation of the contraction of the ventricles. So depolarization means when we we'll talk more about that in neurology, but depolarization means when we create a nerve impulse, and repolarization is when we set the system, the chemicals back so we can make a next nerve impulse. More on that later. But look at that. You don't need to worry about these things. But here, P wave, and atrial excitation or depolarization, QRS complex, ventricular depolarization, and then T wave, and that's the ventricular repolarization. Holy moly. Not done yet. Systole and diastole. So when you look at the heart muscle, the ventricles contract rhythmically. They move blood in small volumes into the pulmonary trunk and into the aorta. Actually, the same amount of blood. It's just the muscles on the left side are thicker because they have to be more forceful because the systemic circuit is bigger, is larger than the pulmonary circuit. But when this continuously contract and relax, so the ventricles contract, the blood gets ejected, they relax. The blood it fills up with blood, they contract, they relax. And so we have these two states. So the state of contraction is systole. The state of relaxation is diastole. Systole, diastole. Contraction, relaxation. Oh, we're also going to have two blood pressures. The higher number and the lower number. The higher number is when the heart contracts. How much force is put on the vessels? The lower number is when the heart is relaxed. How much force is pushed on the vessels at that point? So that's what we measure with the blood pressure. We'll get to that. And then the heart valve, as we said before, they allow the blood to go unidirectionally, so in one direction, and they prevent backflow. They open and close in response to change of pressure. Well, actually, the AV valve closes because the heart muscle contracts and then the strings are held up. But there's still the pressure that has a play in it as well, so they don't flap. We talked about the heart valves, so we don't need to worry about them in this section, but I brought them up again. Some of the similar pictures. But what we talk about in this section is the heart sounds. And so when you actually hear loop up, loop up, loop up, listen to my heart, you hear the valves closing. That's what you hear. Sometimes you hear the blood going through, but when you hear the blood going through, it's a shh, and that's a murmur. They call that a murmur, and that's something wrong. That's not always, but often that's something that's leaky. The valves are not quite doing it well. So let's look at these two sounds. We have a lub sound, lub, dub. So the lub is a little bit higher first. Oh no, look at the dull sound. Never mind, I'm not going to do that part. But the lub is the first sound. And the first sound responds to when the ventricles contract and the AV valves close. And then the dub is the second sound, and the second sound is when the semilunar valves close, when the heart muscles relaxed again. That's when they come into play. Lubbed up, lubbed up, lubbed up. And then we can look at the heart sound, we can listen to them in different parts of the chest because they refer sounds to different parts of the chest, the way they project the sounds. But if we have a problem, we can have a shh, and that's a murmur. So we can hear lub sh dub, lub sh dub, or shlub dub, shlub dub, something like that. Anyway, when we hear them, they're either stenosed, so the valves cannot open, or the valves don't close completely. So we can have two problems with that. We can have a closing problem or an opening problem. But that's when you have to see the cardiologist, unfortunately. And sometimes they don't mean too much. So let's look at the cardiac cycle. That's the events that happen when we have a heart contraction. So the first things we have a ventricular filling. So in that phase, the AV valves are open. The blood flows passively from the atria to the ventricle. Then we have an atrial contraction. That's a little timing there. It's called the atrial kick also. At the end of the diastole, the relaxation phase, the atria slightly contracts to completely fill the ventricles. And they call that about 20% of the filling happens there. And then we have an isovolumetric ventricular contraction. Oh, great. Iso means same. Volumetric means volume. Okay, so the volume stays the same. So this is a time when these valves are closed and the AV valves are closed and the semilunar valves are not yet open. And so that's happening there, the isovolumetric contraction. So we can pull the pressure up and build it up until the semilunar valves open, and then we have a ventricular ejection. That's when the blood leaves the ventricle. And that's about 70 milliliters per stroke. That's a stroke volume per contraction. And then we have a brief period where we have an isovolumetric relaxation when the myocardium relaxes and all the valves are closed briefly before the AV valves open again and we have a ventricular filling happening again. And that's the cycle. I know, it's a little more to it than we think, but it's kind of common sensey. And then this is kind of interesting. You could print that out or look at it in big, make a screenshot of it or something from the video, because you see all the different parts here. You see what the valves are doing, if they're closed or open. You see how the heart looks, where the blood's flowing. You see the pressure. These are pressure numbers in the atrium, in the ventricle. And then these are filling volume numbers. And then these are electrocardiogram numbers. I mean, these are electrocardiogram, and then these are sounds, heart sounds, when the sounds happen. So that's kind of an interesting chart. This is just goofy stuff. Good. And so that brings me to cardiac output. And the cardiac output is the blood volume the heart pumps in 1 minute. And so we know the stroke volume, each pump, we said there's 70 milliliters. That's whatever fits in your palm of the hand, more or less. And that's at rest. Stroke volume here. And then also the other thing we need there, if we want to figure out per minute, is how many heart rates we got per minute. How many of these strokes we got per minute. And so that's a heart rate. That's also about 70 per minute at rest, more or less. So that gives us a blood volume per minute. 70 times 70 is about 4.9 liters per minute. 7 times 7 is 49. 2 zeros on the top. 4900 is 4.9 liters. See that? What's interesting though is we can actually double the stroke volume if we want to, and we can look at that. What is that? Triple almost? Not quite. The amount of pump blood, the frequency of the heart rate. And so if we need to, we can have a 5-time turnover of your body's blood volume per minute. We can go all the way up to 25 liters if we have to. Obviously briefly, but that's pretty flexible. So that's pretty cool. So cardiac output is heart rate times stroke volume. And here we go. That's pretty much all we got for that section. All right, I hope you learned something on this. See you later.